Right, picking it up. We evaluated a couple of Riemann sums. Now that we got kind of the idea behind this, let's take a look at this example. When we learn Riemann sums, we introduce it as this is a stepping stone to the fundamental theorem of calculus. The reality is, though, Riemann sums have plenty of use on their own if you're given limited information. If you don't have the entire function, maybe you have something like the data in this table. This table shows speedometer readings over a 1 minute interval for a professional race car. So let's take a look at that. They're giving us time and velocity. Notice the time is in hours, yet the readings are just over the course of a minute. So when you look at this, right, the 3600 is the number of seconds in an hour. So we'd say they started at 0 seconds and looked at the velocity of the car. It's in mid-race, right? Then they looked at 10 seconds and 20 seconds, right, all the way down to 60, and we can see the velocity of the car at those times. So it's decelerating, then accelerating again. Let's take a look at the questions. Part A says, estimate the distance this race car traveled using left endpoints. So we don't have a function that describes, the velocity of the car, but we do have all these measurements every 10 seconds. So we can think of that as a Riemann sum. And even look at what we're going to try and find, the distance that the car traveled, given the velocity that it was going at each of these times. And then in part B, similar, estimate the distance using right endpoints for that one. Okay. Here it is. Here's that table again, time and velocity. Part A, estimate the distance traveled using left endpoints. Here's what we're going to do. And how does this table connect with the Riemann sum? Think of it on an XY plane. So I'll just draw a quick sketch. So if these are seconds, right, 0, let's say 60, right, there's 30 seconds, 10, 20, 40, 50, okay. So we've got the seconds, and this is velocity. So at 0 seconds, we know it's up at 182.9, right? At 10 seconds, it's at 168. And then I think it's kind of slowing down. At 30 seconds, it's at the slowest speed, just under 100 miles an hour. And then it starts to creep back up, right? We could think of this as, if you can picture the function, we could think of this as left endpoints. So our first region, right, that's actually a right endpoint. My mistake. The left endpoint would go up to where the 0 is and come back down. The left side, the left side, the left side, the left side, the left side. And then this last one, that last point wouldn't be used since we already have that last region, 1, 2, 3, 4, 5, 6. Okay, so if we find all of these areas, we got it. How can we do that? Say, okay, well, I don't have a function, but I already know what the heights are, right? The height of that first rectangle is 182.9. I don't have to plug anything in. I already know it. And I know the width. Well, these are in seconds, but the width is going to be the distance here, 10 over 3600. In fact, the width for each rectangle is 10 over 3600 every single time. So if we wanted to use left endpoints, what we're going to call this L6, say, okay, the height of the first rectangle, 182.9. The The height of the second rectangle, 168.0. The third rectangle was 106.6. The fourth rectangle was 99.8, 124.5, and 176.1, which uses the first 6 numbers in the table. We don't need the last one. The width of each rectangle, again, it's 10 seconds. We're going to say 10 over 3600. We can do that calculation. This is a little bit easier. Okay, let's see here. 182.9 plus 168 plus 106.6 plus 99.8 plus 124.5 plus 176.1. Okay, then times 10 over 3600. What does that give us? I got 383. Doesn't tell us how to round, but 3 decimal places will be nice. Very good. Now, what does that actually represent? 2.383 what? It's the distance traveled, right? If we're looking at hours, miles per hour, this is miles. Which at first is like, wow, it went well over 2 miles in 1 minute. That's pretty good. But a more interesting question is, why is it that when we add up these areas, right, why is it that each one of these areas represents a distance? Why does it represent miles? Oh, okay, check this out. Let's just look at one of these rectangles. I'll draw it here. All right. So we had the axes, right? This was velocity. This was miles per hour. Let's even write it as miles per hour, like that. This, I wrote seconds. It's actually hours because we're thinking of it as over 3,600, right? Well, right, think length, or like length times width, or base times height to find this area. The units for the height are miles per hour. The units for the base are hours. Well, when you multiply miles per hour by hours, what happens? You get miles. So that area, although we're thinking of it as an area graphically, it actually represents a distance, just a linear distance. That's pretty cool. Okay. Let's take a look at part B. Now we're gonna do right endpoints. Same idea, but now we use all the right sides. So I won't do the drawing again. We're gonna use these 6. The first rectangle, its height is there. The second rectangle, its height is there. So we can add all of these up. We're going to call this R6. It's going to be 168.0 plus 106.6 plus 99.8 plus 124.5 plus 176.1 and plus 175.6. And this will multiply by our width, 10 over 3,600 hours. Let's see what we get. Oh, man, okay, adding these up. And times 10 over 3,600. I got a really similar answer, 2.363 when I round it. Really close, that's miles again. It makes sense they'd be close to each other, right? There you go. Okay, very nice. You know about Riemann sums. That's it for our first section, 5.1.